Our first speaker is Ben Kaiser, who will be talking about the lithium pollution in white dwarfs. So please go on.
Oh, in the wrong window. There we go. All right. Hi, I'm Ben Kaiser. I'm a PhD student at the University of North Carolina, where my advisor is Chris Clemens. My other collaborators are listed here on this slide. Today, we'll be exploring the exciting discovery of lithium in white dwarfs and the even more exciting potential science that discovery could yield. We'll be covering quite a few areas today, so I would like to begin with an outline of what we'll be going over. First, I'll provide a brief introduction to galactic lithium evolution, as most of you are probably not very familiar with it. I certainly wasn't before. Then I'll review how white dwarfs can be used to measure the abundances of extrasolar planetary material, as we've seen in several other talks, but just in case people missed it. We'll then see how that planetary material can be used to track galactic lithium evolution. Next, I'll show that this method has even more profound potential related to cosmology. We'll then briefly address potential complicating factors related to geology. And finally, I'll lay out the future of these kinds of lithium abundance measurements. So we begin with galactic lithium evolution. In the Big Bang, only 3 elements were formed: hydrogen, helium, and lithium. That's it. So if we think about after the Big Bang, that's when all of the other elements must have formed, and that's when they did form. So if we think about the lithium to metal abundance, or specifically lithium to iron, at the beginning of the formation of the galaxy, we have the lithium from the Big Bang and no iron, meaning we're doing some number divided by 0, which, as everyone knows, is very large or infinite. And so our model for galactic lithium evolution begins at a very high value on the left here, basically infinity. But over time, iron was formed, synthesized nucleosynthetically, in type 1a supernova and other stuff. And so the lithium to iron abundance ratio decreased over time towards this plateau. You see it ending with on the right of this plot. You probably notice that there are also data points on this plot that don't really match the model much at all in green. Those are from main sequence stellar measurements. There is one exception to that, though, for points on the plot, right? There's the solar point right there that intersects the model perfectly, it looks like. Except that is not the sun. No. It is the sun-like symbol that's used for it, like the little bullseye kind of shape. So it's understandable you would think it's the sun, but it is not, in fact, a measurement from the sun. It's, in fact, a measurement from rocks, specifically a certain kind of meteorite known as CI chondrites. And these meteorites are believed and appear to reflect the protosolar nebular abundances of everything. Well, not everything, pretty much everything, one of which being lithium. And so the solar system lithium abundance is derived from CI chondrites and not from the sun, unlike most other elements like calcium and stuff. So this faux solar point on the lithium to iron abundance plot is actually the solar system abundance of lithium derived from CI chondrites. You're then naturally wondering, I assume, that where is the sun on this plot? Well, it's not technically on the plot. It's off the bottom of the plot if you measure it from the solar photosphere for the lithium, because it's 2 decks lower than the CI chondrite abundance. So then why do we use rocks instead of the sun for our solar system lithium abundance? Well, the reason is we're pretty sure the sun burnt some portion of its lithium through nuclear fusion, because lithium is incredibly easy to burn in nuclear reactions. And it's likely that these other main sequence stars also have burnt some portion of their lithium. So why is everyone using main sequence stars to track galactic lithium evolution if we know the closest main sequence star is not trustworthy for this measurement? Because they didn't really have any other option. Switching gears slightly, we will now discuss how white dwarfs can reveal the abundance of extrasolar planetary material. Okay, sorry. Earlier this year, our collaboration identified lithium for the first time in a white dwarf photosphere, J1644. Why is this not responding now? Okay, let's go mouse. We also identified potassium for the first time in a white dwarf photosphere as well. And we identified lithium in a second white dwarf photosphere, J1330, in the same effort. Note that I've placed colored stars next to each white dwarf name. These colors are the same colors that these white dwarfs will be represented with on plots later in the presentation. Oh, sorry. I don't know if this is making like little black boxes or whatever, but I'll hide that. There we go. Very soon after our paper was published, like really soon, like almost the same time, Hollins et al. Published 3 additional white dwarfs with lithium in their photospheres and an independent re-identification of the lithium in J1330's photosphere, which is the bottom one in this figure. So that was the second one from the last slide. Again, I've added the color markers for each white dwarf to show what color it will be on future plots. Okay, so we've got lithium in the photospheres of 5 white dwarfs now, but so what? Lithium has been found in thousands of main sequence stellar photospheres. So why is this a big deal? The key difference is the source of the lithium in the photospheres of the white dwarfs. This lithium and all the other metals in the photospheres of the white dwarfs are from extrasolar rocky planetary material that the white dwarfs accreted fairly recently. So white dwarf surface gravity is strong enough that only hydrogen and helium should be in the outer layers. Therefore, the detection of heavier elements means they must have recently fallen into the photosphere. This accretion can be crudely broken down into 3 phases: increasing, steady state, and decreasing. Increasing phase is essentially when accretion has just begun. Steady state occurs when accretion and diffusion are in equilibrium, and it occurs after accretion has been going on a while. Decreasing phase occurs after accretion has halted or dramatically reduced in intensity, but we're going to just think about it stopping for simplicity's sake today. And as with the colors on previous plots, this time I'm showing the different symbols that represent each phase on future plots. Note that the decreasing phase arrow is a slightly faded version of the other color. These symbols also, for the record, represent the abundance of the original planetesimal that we would infer for a given accretion phase, and it differs element by element. Also, the length of the decreasing phase arrow corresponds to accretion halting 5 calcium diffusion timescales prior to the moment we measure the photospheric abundances, which is the extreme case of the decreasing phase. The accretion phase is much more likely to be closer to the tail of the arrow than to the arrowhead. Also note that we're only taking one measurement in each of these scenarios. We're taking the one measurement for the photosphere of a white dwarf, and all these different accretion phases are being used for, are basically, we don't know which phase it's in necessarily. So depending on the phase, from this same measurement, we infer different planetesimal abundances, basically. So now we have extrasolar rocky planetary material for which we have lithium abundance measurements. Well, remember this plot, the one where lithium evolution modelers were forced to rely on main sequence stars everywhere but the solar system, which was the only location where we could get lithium from rocks. Here's a version of it with the lithium abundances that were not altered by nuclear burning of lithium. The CI chondrite point's the only one remaining. But wait, sorry. We have all those extrasolar rocky material measurements from white dwarfs we could add to this, material analogous to CI chondrites. And we can see that the lithium abundances of the extrasolar planetary material generally track with the expected trend for galactic lithium evolution, which is very different from the main sequence stars, with the exception of a slight age mismatch. So it's possible that that model that used the 12 gig-year-old disk is part of the problem. Maybe it's white dwarf total ages, realistically. So if you use a slightly younger disk line, which is the stashed one, it can move to a slightly nicer intersection with the white dwarf provided points. But I mean, what can you expect? The lithium evolution modelers had to rely on mid-sequence stars until now to try to do this, and we're attempting to map that over. So that's a neat application of the lithium abundances from these white dwarfs that might let us get a little more money from grants, but that is a mere appetizer of the potential implications of measuring lithium in extrasolar rocky material. This is the spite plot. It's in pretty much every paper about lithium abundances. The y-axis shows lithium to hydrogen abundances in log scale with that plus 12 added on. The x-axis shows the solar normalized metallicity using iron. This dashed line through the middle and up to the right is the galactic evolution of lithium abundances, or predicted rather. Whoa, modeled version, sorry. Notice that it starts from this plateau. That's because that is the predicted amount of lithium formed in the Big Bang. Essentially, it is suspected that the amount of lithium in the vicinity of the sun and the galaxy was unchanged until some metallicity near -1, at which point lithium enrichment mechanisms fired up and started making some more lithium. However, if we zoom in on this plateau, we see that the main sequence stars do not quite reach up to the predicted Big Bang nucleosynthetic lithium abundance. This discrepancy is known as the cosmological lithium problem. This plateau, that not reaching up to that value, is not new. After Spite and Spite in 1982, of Spite plot fame, rather it's named after them, tried to measure the amount of lithium formed in the Big Bang using metal poor main sequence stars, dozens or more astronomers followed. For nearly 4 decades, paper after paper has attempted to test or derive the Big Bang nucleosynthetic lithium abundance, but they all came up short on lithium compared to predictions of Big Bang nucleosynthesis. But this is not altogether surprising. They were using main sequence stars for their measurements everywhere except in the solar system, where they used rocky planetary material. If only there were some means of using rocky planetary material from far in the galaxy's past instead of main sequence stars to get the lithium abundance. Well, we have those now. If we plot our lithium abundances from our white dwarf provided rocky planetary material on this plot, we see that they don't really seem to suffer the same problem as the main sequence stars. Take a moment to think about this. This year, well, the end of last year, because that's when our paper was published digitally, but that was the first time in 4 decades of people making this plot that it included more than one data point using rocky material. Unfortunately, we don't know the metallicity of our white dwarf systems, which is what the diagonal lines are basically encompassing. So the correct answer, if you will, for each white dwarf lies somewhere along its respective diagonal line and vertically for accretion phase as well. So they're rather large uncertainties at the moment, unfortunately, but it's got a lot of promise. There are, however, some potential complications relating to planetary processes that I would be remiss to not discuss, which we'll call planetary processes geology for sake of consistency, I guess. It is worth first discussing volatility. Basically, the higher an element's condensation temperature, the harder it is to keep out of a rocky planetesimal you form. Conversely, the lower the condensation temperature, the easier it is to keep an element out, or to remove it in collisions, as collisions heat whatever are involved in them. So sodium, for example, is the easiest element to remove of the ones we'll be considering, and calcium is the hardest to get rid of. It was suggested by Hollins et al. 2021 that all of their white dwarfs accreted continental crust, and that differentiation explains the lithium overabundance compared to CI chondrites rather than cosmological effects. We can see here that the lithium abundance does vary in different rocks in the solar system, and continental crust does have the most lithium of any of the rock material I've managed to accrue from literature. But all of the white dwarfs of lithium detections appear to likely have too much lithium to be continental crust. They are all clustered above every solar system object. Most notably, J2317, orange, which is strongly suspected to be in steady state or increasing phase due to an IR excess found by Hollins et al. This one is multiple sigma over-enhanced in lithium relative to calcium when compared to continental crust. So just by this alone, continental crust cannot fully explain all of the rocks accreted by these white dwarfs. As kind of a nuance point here, we're not claiming J2317 orange has more lithium than the meteorites in the solar system per se. Rather, it has less of everything else in it, because remember, those weren't synthesized as much early in the universe. If we instead look at potassium and sodium relative to calcium, Sodium and potassium have relatively similar condensation temperatures, you can see in the table. We can see that J1644, red, falls right near the CI chondrite point, as would be expected for rocky material that has not had its lithium abundance substantially altered, because potassium and sodium are even easier to remove than lithium. If it were continental crust, J1644, red, would have a dex level potassium enhancement, and it does not. J1330 purple and J2317 orange are only upper limits in potassium at present. Eventually, with better measurements, that should change. But unfortunately, these upper limits can't really exclude anything in the solar system. It just basically indicates there's something. LHS 2534, blue, is up around continental crust, though. So maybe it could be continental crust based on just these abundances. But if we look at that same star, LHS 2534 blue, in calcium, iron, magnesium space, we see the inverse situation. It is nowhere near continental crust. It is, in fact, down among the primitive material, like CI chondrites. So this is certainly strange. It is now worth considering if there is anything unusual about LHS 2534 blue that could maybe cause such odd results. And there is. LHS 2534 blue is magnetic with a magnetic field strength of 2.1 megagauss. So it's conceivable that the magnetic field is doing something weird to the models or the accretion process or something else. In any case, it seems that using the sole magnetic object in the sample to define the material accreted by the other 4 non-magnetic objects is a bit treacherous, as demonstrated by the contradictory material identifications for different elements for this white dwarf. So where do we go from here, though? So since neither differentiation nor any other geological process can explain the lithium overabundance of J2317, orange, and there is minimal evidence to support the other 4 objects or continental crust material, it follows that the lithium overabundances are primarily the result of the predicted galactic lithium to iron evolution trend. Therefore, these measurements can be used to track the galactic lithium evolution relative to metals. And with further refinement, they should eventually be able to test Big Bang nucleosynthetic lithium predictions and potentially resolve the cosmological lithium problem. So where do we go from here, though, in terms of actual steps? There's a lot of work to be done to get to the point of testing Big Bang nucleosynthetic lithium abundances using these white dwarfs. Number one, as everyone probably already suspected at the beginning, we need more lithium-polluted white dwarfs. We also need improved diffusion timescale grids that go down to 3000 Kelvin just regularly. The most recent ones from Kaiser in 2020, I believe, go down to 5000. Also, there's like the improved diffusion method. Can't remember the paper from that one now. That needs to be used for all the other elements. We need to constrain the accretion phases of these white dwarfs because that's the vertical positioning in the spike plot with the faded arrows as well for decreasing phase. Ideally, we would get rid of those and just have a single, relatively well-constrained range. We also need to measure the potassium abundances in addition to sodium and calcium for lithium-polluted white dwarfs, because that enables us to constrain the type of material accreted, and the accretion phase also constraining that relies on additional elemental abundances. We also need to devise a correction basically for the nebular to get to the nebular lithium abundance for a given accreted planetesimal, because the lithium abundances of even relatively primitive meteorites are slightly different than CI chondrites, and the odds of accreting exactly a CI chondrite are pretty low. So there are tenths of dex around there level alterations that can happen or could have happened that we need to, as part of the identification material and accretion phase, basically devise some sort of formula that relates the other elements to lithium to recover what the CI chondrite analog lithium abundance would be for a given system. Probably most importantly, we need to constrain the metallicity of each white dwarf system. We talked about this in our supplement way at the end. Currently, what we're using are kinematics, kind of, for a really weak constraint on metallicity, as you obviously all saw on the spike plot with our giant, very large range diagonal lines. Ideally, in this fantasy world, we would have each white dwarf in a wide binary with a main sequence companion. So we could use the main sequence companion to get the metallicity, that we would use the lithium to calcium ratio to rescale from lithium calcium ratio from the body that polluted the white dwarf to rescale by the metallicity from the wide binary companion to get a lithium to hydrogen ratio analogous to how we do it for the solar system. Unfortunately, none of the current 5 white dwarfs have any wide binary companions, let alone a main sequence one. So we're out of luck there with these ones. So the more lithium polluted white dwarfs will hopefully yield several with wide binary main sequence companions. But this is kind of a, if we find enough, we might get lucky. It's not really a plan. The third potential route would be an age metallicity relation that extends to these extreme ages near the beginning of the formation of the disk of the galaxy. Unfortunately, age metallicity relations from previous years of the effort have yielded no such luck. There's a bunch of scatter in it, which is partially due to multiple formation histories, radial migration, take your pick. It's pretty difficult. So another very challenging thing to tackle there. And lastly, there's this kind of lurking problem of the lithium lines in the atmospheres are slightly too narrow compared to the model lithium lines. Part of that could be related to the lithium line modeling currently not using the unified line theory line profiles like the sodium line does currently in these white dwarfs. That's related to the availability of some sort of computation that I think Simone Bouin said we need some sort of computational chemist to do. So if anyone, chemists that can do that, try pestering them to do that for us. So in conclusion, galactic lithium evolution measurements are best if based on rocky material. That material has been CI chondrites for the solar system, and it could be rocky extrasolar planetesimals accreted by white dwarfs for elsewhere. And the most promising route to test Big Bang nucleosynthetic lithium abundance predictions and potentially resolve the cosmological lithium problem is via measurements of lithium polluted white dwarfs. Thank you for your time and putting on this conference as well.
Okay, thank you for your presentation. It was very, very interesting, really very interesting work. And also it's nice to see for the first time points above the Big Bang nucleosynthesis values for those, which we expect. So let's see. Do we have here? We have a question by Pierre Manuel Tremble. He's asking if you consider that did you consider that LHS 2534 may have accreted more than one planetesimal? Hence, the composition may not fit one particular solar system body.
Do I consider that? I have considered it. I mean, yes, you could probably take some amalgamation of different things from around the solar system to make almost any abundance, except for higher lithium values, though, to a certain point. So, I mean, yes, but if you look at that one, it still is clustered up here with the other ones. There is no object in the solar system you can put in here to get higher lithium to calcium, which I realize with the error bars it overlaps continental crust, but there's still most likely this lithium effect from evolution of the galaxy. Also, adding in another body at this point doesn't really benefit us necessarily. I don't know. It seems odd that the magnetic one's the one you have to throw a second thing in to fix the abundances, and none of the other ones appear to require this.
So do we have more questions from? I don't see. If you have one, you have time. We still have 1 more minute before it's 25 minutes. So if you have one more question, if there are none, I may take the time to ask one myself. So the age of the white dwarf, how have they been derived them? How did you derive them?
Yeah, so we discussed this in our supplement at length, but basically we use the uncertainties from the model or from the parameters reported by each paper, so like log G, T effective, to do a Monte Carlo into the initial final mass relation from Cummings et al. 2018 that give us progenitor masses, which we put through the Hurley Hurley and other authors, 2,000 polynomials to get main sequence plus helium burning lifetimes of the progenitor, which is added to the cooling age of the respective Monte Carlo white dwarf to get a total age. And then in those, we take the maximum value, like simulated white dwarf bin as the central value, and then a 68% interval on either side of that.
Okay, so which initial final mass function did you say you were using?
Cummings
Sorry.
et al. 2018.
Okay, and so there you have.
We also Monte Carlo that one's uncertainties in it.
And so for the progenitor times, you were using like a solar. I mean, you need the metallicity. That's why I'm asking.
Yeah, we're using solar metallicity because the cooling time scales use solar metallicity, so we wanted to at least be consistent with that. But yeah, it's unlikely they're actually solar metallicity. But
okay, so okay, that would be okay, perfect. So
yeah.
there are one more question. So is given that these are low temperature white dwarfs, how susceptible do you think your results are to modeling systematics in determining abundances?
Oh, and the abundances? Oh, I don't know if there are that many for the abundances. The masses and temperatures, there are probably a lot of dangers because we get some lower masses than probably should. For example, 1824 has low mass. It's like 0.3. Yeah, the abundances, I don't think those ones have, at least when you do relative abundances, much danger for substantial systematics. Maybe in like to relative to helium or hydrogen abundances, there could be a danger for that. But yeah, like lithium to calcium, lithium sodium, sodium calcium, those are all relatively
okay.
robust.
So
definitely less than a dex.
I realized that I jumped over some of the questions because I just saw the last one, and there was one before, which were, are there magnetic effects on the lithium lines? Do you see any magnetic effects?
Oh yeah, it's split. I think it's Zeeman split. Yeah. Well, in the magnetic white dwarf, yeah.
And then, of course, this J.J. Hermes' comment is about the cosmic ray spallation providing the lithium enhancement.
So
for the strongly magnetic white dwarf. So yeah, that's more of a comment.
You mean, well, cosmic rays, you mean charged particles in the magnetic field of the magnetic white dwarf? Because cosmic rays themselves are unrelated to the white dwarf. They would be just out there. So that would be the same for all of them. But it'd have to happen at some point when it's spread out and the disk lifetime's not long enough to spall an adequate amount of lithium. It's less than 1/10 of a dex, assuming current fluxes.
Okay, so I think we can move to the next speaker. So thanks again for the presentation, and also it's very nice work. It's really interesting.